All right, cool. Welcome, guys. Nice to see you guys, and good morning, or whatever time zone you're in. So if you guys don't know, just want to bring your attention to the course timetable, which is just the fourth item down here. And just to give you guys an overview picture as well, the lecture times, I'm still simming through them if we change or not, but so far here, I'll just, in the timetable, it's just kept as the way it is. I've color coded them so it's easy to read, hopefully. So as you can see, the schedule is homeworks are usually due on Sunday. I also want to sort of, sometimes I want to try to explain the logic of why the admins are sometimes the policies or the things I chose the way it is, the rationale behind things, because it'll make it more understandable for you to see, and it doesn't seem as random. So yeah, hopefully as you know, the homework one is already up. So normally you're given at least 6 or 7 days to do it. It takes around 3 days to grade and stuff like, or 3 days or less, depends on the TAs will do a lot of the grading. So that's why the last day I shifted a little bit earlier, so that hopefully if the TA can grade it within like 2 days, you can get a final marking. So they'll grade, so you know maybe on Monday or Tuesday, a little bit before the final exam. So that's the reason for that slight shift. It will be the same due at 11:59 p.m. just at the end of day, basically. Okay. And if we look at week 2, so that would be where the first test will be, the first topic test, and it will cover all the material. So from lecture 1 to 4, so I put in brackets what is going to be covered. So in general, as you can see, the test will be on Tuesday. If you probably see on the course syllabus already, you see that the topics are roughly split into 5 sections. So that's nicely split into 5 weeks. I think usually being optimistic, I'll probably be able to finish by lecture 18. So lecture 19 and 20, either is a buffer. Sometimes I think things might overrun. It depends on how much other things I elaborate on. So I'll have a lesson of buffer, and also maybe one of those days can do a review session for you guys as well. So as you see, the test is intended, because I'm bringing this up because there is a question about the topic tests, and that's a good time because today you'll have your first discussion session. So today you'll do basically a trial run so that you'll know exactly what to expect by next Tuesday. Right? So of course, if I want to cover all 5 topics, since it's a topic test, then I need 5 tests. So the last one would be just on the last day. Right? So that's usually what the Tuesday discussion sessions are for. The Thursday's discussion session is basically generally try to review everything during this week, right? So for example, discussion session 4 reviews the material here, and also we'll give you a problem to solve. So you can have a grouped discussion environment. Basically, roughly speaking, is in the beginning, your TA will probably explain a little bit more, but in the beginning, we'll give you a problem, give you around 5-7 minutes to try it yourself, and then we'll split into breakout rooms, and then you can talk amongst yourself for another 5-7 minutes-ish. And yeah, and then we'll bring you back together, and then TA will go through the solution, something like that, and answer any other questions you have, just conceptual or whatever, right? And hopefully that will prepare you, each of the Thursdays will prepare you for the coming homework. As you know, here's a little study tip if you want to succeed and do well in the course, as many of you have said in your comments, in your survey, which is a great goal, which is a great job. Physics is one, as you probably know already, it's a subject where you have to do a lot of practice, and it takes time to absorb the concept. And one thing you probably already learned about physics is you realize understanding the concepts and able to do a problem is 2 different things. So in lectures, we're mostly, I think, my job is in the lectures is to explain to you the concepts and set it up and hopefully show you why it is interesting, because as I mentioned yesterday in our first lecture, that's one of my goals, to hopefully show you the interesting side and how to do physics well, and how to utilize to think like a physicist, and so that physics would become a simple topic for you, hopefully after this course. Right, so it takes time to develop that, and it will never work if you try to batch all the content in 2 days and try to do a homework. So having a regular schedule like this, I highly recommend. Right, so yeah, so that is basically the plan, and of course, and on the last day, basically, because if everything goes according to schedule, even if I overrun for 1 session, they should pretty much be fully covered, and you'll be ready to do that final test on it. If I do overrun or whatever, the final test I will not test things on the immediate day before. At least give you a day to study. All right, so hopefully that gives you an idea. That is on Canvas. So also, you guys are using Piazza very well already, so good job. And I think a lot of you will be easily get 5 posts over the whole course, right? 5 or 10 posts, and you'll get 5 or 10%. It should be I think everyone should be able to get it, right? All right, so yeah, so here's a question someone asked about whether it's open book or not. So really, I just want to emphasize this, because I want to elaborate on this a little bit, is the goal for a topic test is really to treat it as like a mini exam, and also a low stakes sort of self-evaluation component for you, so you can see how well you're doing. It's low stakes because all of the topics test together is 25%, so 4 of your best tests will be counted. So 4 of your best work will be counted. Each of them would just be 6%. So even if your best work is not your best work, it's not a big deal if you didn't do too well on 1 or 2 of the topic tests. I want to make that that it counts for something, but it's not the end of the world if you don't do well on it. Personally, I don't learn well. I think personally, from my experiences, physics takes some time to marinate and absorb, right? So giving a test immediately the week after you cram everything, you learn everything for the first time, is actually quite stressful. So I try to make it as low stress as possible. On that line of logic, that's why I'm making it open book. However, in the final exam, the purpose of a final exam is because between the final exam and the last day of lecture, you'll have almost a full week to study for that. So by that time, at the very end of the course, the final objective is to know the stuff well. We mentioned it's coming to college is to learn how to think, learn how to learn on your own. But so here we're presenting you with all the course materials, and you have to, by the end of it, you have a deadline there. You have to know it, right? So so that will not be open book. But for the intermediate sort of self-evaluation topic test, I'm trying to make it a little bit less stressful, so it will be open book. And also open notes. The only thing you're not allowed is you can't do web surfing. You cannot go on Google and ask questions and stuff like that. All right, here the question was also asking for the extra material to study. What is the best way to study? So the study method is this. Basically, the homework, every component that is graded. So these are the 3 components in the course that is graded, right? So 25, 25, 50. So everything, I want to make them as similar as possible. In particular, the test and exam will be in a very similar format. And you'll see a little bit more today, as Ye will explain that. The test basically consists of short answers and long answers. Right? Short answers are open response questions. Short answer questions are basically just 1-line answers, just to ask if you know this or not. What is Newton's second law? Write down F equals ma, and that's the end of it. Right? So it's probably just 1 point or 2 point types of questions. Okay, and the open response are proper questions, and those will be very similar to the homework problem. So the homework I basically pick from the end of the chapter most of the time, and if you like, basically just go through all the other ones that I did not assign, and that would be the best way to prepare for the tests and the exams. Okay. Right. Yeah. Let's see if anything else. Extra practice problem, as talked about that. Formulas. Yeah. So for the topic test, obviously you can just look at the textbook for your formulas. Having said that, this is what I recommend, especially for those who really want to do your best and get a really good grade. If you want to strive for an A, this is what I highly recommend. Treat it as not open book, right? And treat the textbook there as a backup. Treat it as if you forget something, or if you're slightly unsure, if you forgot, like, oh, is it F equals MA or is it F equals M divided by A? If you're 90% sure but not quite 100%, then you can just quickly scan through the textbook to look and verify it for yourself. So this is what I recommend. And also another thing is, really don't rely on that open book. First of all, in the final, you want to mimic final exam. That's number 1. And number 2 is there is a time limit. And if your mentality is to rely on the textbook, I'm afraid you probably might not have enough time. You should have enough time to do it, but it's the mentality, right? So if you treat it as closed book, then you study better, then you'll definitely have time. So if you study well and you treat it as open book, technically you'll have enough time, but my worry is if you treat it as, if you are too relaxed and treat it as open book and you don't study well enough, then you probably won't have enough time. So the test is not enough that you can not study at all and rely on looking for answers from the textbook for the first time. If that is your strategy, you will not do well in the test. Right? Okay, so that is the recommendation. All right, so yeah, I'll talk a little bit more about final exam later on. I'm leaning towards the cheat sheet, but so the point of the cheat sheet is instead of giving you a formal sheet, I think cheat sheet makes you'll have to, for those who never used a cheat sheet before, the idea is you beforehand, when you're studying, go through your own lecture notes, the notes you take or the textbook, and then write out all the formulas that are relevant. Hopefully by then you'll have done enough topic tests and done enough homework problem that you'll pretty much see a pattern of the questions, right? So you know the type of things that'll be given. I'll talk more about that, so don't worry too much about it at the moment. I promise it is doable. Everything should be doable for you, right? But so when you make a cheat sheet, so that's writing out all the formulas you need, that is a good way to study. For me, myself, in some of the course, I did my best in some of the courses that actually use the cheat sheet format because it forces me to sort of rewrite my notes, reorganize things. So I hope that will be, but I'm still gonna confirm this in the future. Okay, all right, so let's get into today. So first of all, I want to give you guys maximum of another 4 minutes to get to talk to each other. I think it's always, I don't have too much time to allocate, but I still want to allocate a little bit of time. And sort of for these chances of remote learning, it's just great to get to know people who are on the same boat with you and get to know some friends. And I encourage you to learn each other's names so you can hit each other up on Slack as well. You can create a little group, or if anyone seems particularly friendly, you can direct message them, you can DM them. If anyone is annoying you, Slack is great. You can mute the channel and you don't have to worry about them. In fact, I was actually talking to a fellow course mate, and she's teaching her course as well, and she was saying her students actually set up a Discord server to study together, which is great. So if you don't want to use Slack, feel free, whatever you like. Right? All right, so what should you discuss in the next 4 minutes other than that? I will give you 3 questions to discuss. The first one is just a quick recap. Do you remember from 3A, what's the difference between weight and mass? Right? Hopefully it takes you 5 seconds to answer that. And then 2 more questions. Number 1 is, what is the goal of physics? So I don't know if you think about this at all. What is physics about? What is this subject for? Because that would very well give you an idea why we're studying these topics that are coming up. Sure, it's good to know about fluids, it's good to know about heat, and it's good to know about electricity and magnetism, but how do these things fit into the bigger picture? And why do we care about fluids other than taking an MCAT or whatever? Why do we care about this? What's so interesting about it? Right, so that is, so give it a minute or 2, bounce some ideas. What do you think? Can you summarize physics in 1 sentence? What do you think is the goal of physics? Has anyone taken an econ class before? Do you know the central question in econ? Economics, they 101 kind of thing. They sort of lecture 1, they will tell you the central question. They are very organized with this. They'll tell you the central question of economics is just 1 sentence. It's trying to satisfy unlimited wants with limited resources. This is so ingrained in my mind. So can you think of what physics is about? And now leading to fluids, the final question is, why, if someone asks you, say if you're walking down the street and you bump into someone and they say, oh, by the way, can you explain to me why things float on water? I don't know if that would happen, probably because we can't really go out nowadays. But if someone does ask you that, how, as a physics student, as a student who has taken a physics course, how would you answer that? Of course, we haven't gone through the lecture yet, but yeah, let's bounce some ideas off. So I'll give you 4 minutes from now. Yeah. All right, good. So welcome back. Let's take care of the first questions first. So weight and mass, what's the difference? Very good, good. Good, amount of matter and the pull of gravity. Let's see, is there any other answers? Force of gravity, very good. I like this word. So can someone put in the chat what is the units for weight and what is the unit for mass? Good, newtons, force, it's a newton, and grams or kilograms. Someone said gram. I will try to encourage you to use kilograms for physics classes. So we're going to stick with SI units, which is the international standard, international, whatever the French word of that is. The international standard units for physics will be kilograms. It's also called the MKS system, colloquially, the MKS, which is meters, kilograms, and seconds, right? Everything so these are the SI base units. So everything else, newtons is also SI units. So, but it is a composite unit. So it's made out of meters, kilograms, and seconds. So you can build up composite units from the base units. Kilonewtons will not be the SI base unit, but newtons would be, because kilonewtons, which means 1,000 newtons. So you have a random number in front of newtons. And newtons is built out of MKS. In fact, it should be kilograms, meters, and seconds to the power of -2, right? So, or over second square, something like that. So newtons is it's a lazy way of writing this chunk, basically, because as you very much learn in our class, physicists are very lazy animals. So having to write every time, you know, meters, kilograms, meter per second square, it's so much work. We invent a new symbol. But 1,000 in front, that's a random number we put in front. That's not made of MKS. Right. Just to comment as well, a lot of you also will do chemistry courses, I know, which is sometimes causes a problem, because in chemistry, it's much more conventional to use CGS. It's actually a more old school way. CGS used to be that would be centimeters, grams, and seconds. That is the more historical way of doing it, but the more modern way, it's shift to MKS. And sadly, try to use MKS, there is a lot of benefits in problem solving. And then, good, what is the goal of physics? What ideas do we have? While you're writing on the chat, let me explain. Sometimes physics seems boring to a lot of students. And as you know, it's part of my goal to try to make physics interesting to you, right? It seems boring. It's because there's nothing worse than hearing someone tell you a solution without knowing what the question is. I'm sure you have this experience. If you walk into a discussion session, let's say if you happen to walk in 5 minutes late and the TA is already going through a solution and you have no idea what the question is, and you're sitting down for the next 10 minutes listening to a solution without knowing what the question is, that is the most boring 10 minutes of your life, trying to go through all the nitty-gritty, the nuts and bolts, the tiny details of, oh, you have to integrate this, you have to move this around, and what are we doing, right? So it's really important to understand what is the goal of doing something. What is the question? Why are we studying physics? What are we trying to answer? Why do we care? Once you know that, it will be much more interesting to you. Let's see. To solve problems in real life. Good. Yeah. How the universe, nice, I like that. How everything happens. Good. Very good. I think all of them are correct. Good job. All right. So personally, let me quote the most ambitious one out of your suggestions, how the universe works. That's basically how everything happens, right? How the universe work. That's a good way of putting it. And of course, this just makes it sound more fancy, but to break it down, it's how does things around us work? Around us can go from the smallest of atoms to the largest of cosmology, right? How's the universe? Everything is part of trying to figuring that out. To solve problems is real life. It's definitely a subset of this. All right, so how do we do this ambitious task? This sounds very ambitious. So here's what you might know a little bit less is every single problem in the physics, anything you can ask that is related to how the universe works can be translated into how things move. Into a very almost boring question of how things move, right? I'll give you an example. First of all, in 3A, you learn about kinematics. Right? This is obvious, okay? So this is obvious. This is clearly about how things move. It is kinematics in its Latin roots basically translate to kin means motion. Matics is like mathematics is the subject of motion, right? That's obvious. All right, but what about other things? So you can ask questions like, why does the sun rise? That is really basically about how the sun moves. Technically, the earth moves around the sun and creates the illusion that the sun moves around the earth. So that you can see, I can translate that question. For example, why do we have planets? This sounds like nothing to do, not why, how did the planet move, but why do we even have planets? It sounds like it's difficult to translate to how things move, but you can, because you have planets in one sentence, it's because all the dust, all the rocks and debris in the universe attract each other because there's a universal phenomena called gravity. It's basically everything pulls on everything. That's what gravity is about. We are being pulled onto the Earth, as well as every single dust particles, atoms in the world, and they start colliding together, and then they will become a big rock that floats in space. That's how planets formed. Now, sometimes they collide more. If it collides a lot, this heats up, and if it heats up a lot, it starts to burn. This is not the complete picture of how a star or the sun comes alive, but it's on a cartoonish idea, it is. So the idea, if you know exactly how these little particle moves, you can actually figure out where do planets and stars and galaxies come from, right? So how about another more ambitious task? How about how did the universe begin? Right, so again, how would you translate that to how things move? I can do that because how do we even know the universe has a beginning? The idea is we start looking out in the sky and we saw all the galaxies are moving apart. Right, so they're moving apart. First of all, there's motion there already. So it seems like our universe is expanding, right? So if it's expanding, that means if I turn back time, then once upon a time it is smaller and everything is more together than spread out. And at some point, everything must be so small, because why would they stop unless there's some external deity that starts stopping things from colliding? If the world is left to its own, it should go all the way back to an origin. At least that's the first simple guess, right? That's your first hypothesis. Why would you invent something else if you have no knowledge of that? So if you extrapolate the data, that's what it tells you. So it's basically, if you understand everything about the motion of galaxies, that's how the universe, you can infer back in time what happens, and at the same time you can infer back all the way to the future and what will happen in the future as well, right? I have a few more examples, but I'll sort of skip them, and let's go a little bit more down to earth, to real life, to our daily life. How about how does light work, or turn on a light bulb, right? That seems like a very practical problem. I can translate that as well. That is basically the motion of electrons. So I'm not going to write out too much things. Electrons go through wire. As the electron goes through wire, there's friction. Friction heats up. So if you make a certain point of the wire more friction than the other, so it's very difficult to go up. Friction causes heat, and heat causes light, and that's why light bulb will shine. We'll talk more about circuits and light bulbs in the third or fourth week of the course. So as you can see, that can be translated into how things move. And finally, a part of the course as well, heat. You might think, what does heat has to do with that? Well, heat is the vibration of atoms, right? It's basically vibration of atoms. So basically the question comes down to how does atom move inside elements, inside materials, right? I can go on forever, but I can challenge anyone who throw me any real life question, I can translate to how things move, right? So now we have the question. We have the central question of physics, right? How things move. What is the answer? Well, this is the answer. This is what I call the holy grail of physics. A function, x of t. What does that mean? It is x, let's assume we are living in one dimension first. X is every coordinate on the in our universe, basically. If we are in 3 dimensions, that will translate to x, y, and z. Right? So you know the position, let's stick with 1 dimension first. If you know the position of an object at every single time, you know its whole history and future as well. So that's why it's so any of these questions over here that I wrote can actually translate down to finding out what is the x of t of that object. What is the x of t? There's a name for this actually. This is called the function of motion. It's a function of motion. So to find the function of motion of the sun, to find the function of motion of dust particles that make up the planets, to find the function of motion of how electrons and atoms move, this is the idea. Now we have our goal. Our goal is to find x of t. How do we do this? Well, as you know, that we have the idea of velocity, right? Velocity is basically, the definition is basically the rate of change, how much x changes with time. So you can flip this around and say x is the integral of this velocity function instead of the position function. Sometimes this is also called a position function. So if you know v, you'll be able to know x. All right, so I've translated my question from finding x to finding v. Now, how do I know v? Well, let's push this one step further. We know that velocity is how much sorry, acceleration is how much velocity changes. So velocity is the integral of the acceleration function of an object. So if I know A, I'll know V. Now, probably some of you can see already where this is going. How do I know A, right? If I know A, I know V. If I know V, I know X. How do I know A? That probably this comes to your mind, right? F equals ma. So if I know the mass of the object and I know all the forces on the object, right? So sometimes you actually label this F total or F net. Let me write that a little bit bigger. F net. Total is because if someone pushes you from this side and someone pushes you from that side, the net force is 0. You won't have any acceleration at all, right? So well, I sometimes use the word net force or total force interchangeably, right? So this is basically 3A, everything you learn in 3A, the point of why you learn things in 3A. And in 3B, we're going to take this concept and apply to, like I say, fluids, heat, and other real life problems that we're going to solve, okay? All right, so that is the goal. Now that things are in context, you know where we're getting at. Let's do a quick recap of the Newton's laws because we are going to use them a lot in this course, right? So you know there are the 3 laws of motion. And I think most of you can recite this in your sleep. The first is the law of inertia. And if you cannot recite this in your sleep, that's your next job. The next is law of acceleration. And the third law is law of reactions. I made up the second one. I don't think that's official, but I'm going to call it that. All right, so very simple. I think we should know this, but quick recap is, so the first one addresses what happens if the net force is 0. Okay, so net force, it's always good to label that. So if the net force is 0, it says the acceleration is 0. Basically, there's no acceleration. The second one addresses what happens if the net force is not 0. And the third one addresses what if you have 2 things pushing on each other. So if you have force from 1 on 2, object 1 on object 2, and you have a force from object 2 on object 1, what happens? And the answer is the magnitudes are equal. So the magnitudes are equal, and the direction is opposite. And the second law says that if there is an overall net force, right? So if it's not 0, then there will be an acceleration. The acceleration is given by taking your net force, taking your net or total, right, and divide by m. Okay. This is more ugly to remember. That's why we write it like this, and it's easier to remember. However, you really, if no one told you this before, you really should interpret Newton's second law this way. Now you know why. Because imagine if you have an equation, A equals B plus C like this. The object you're trying to solve, do you put it on the left or do you put it on the right? The convention is to put the thing that you want to solve on the left, right? So out of F equals ma, which one is your goal? Which one is your ultimate aim to find? And as from this discussion, we now know the goal is to find A, because the A will lead us just by doing a little bit of calculus. It will tell us our holy grail of the function of motion, right? So that's why everyone should, so technically this is the way you should write Newton's second law, not F equals ma, but this is very ugly to remember. F equals ma rolls off the tongue easier. Okay. So what is also, actually what is force actually? Let me pull back a little bit. Let me write down the definition of force. The definition of force is basically a push or a pull. Okay, it's that simple. It's a push or a pull on an object. And one thing that you want to learn is that anything in contact, with your object of interest will provide a force. Okay. So if I have a box and I'm pushing it like this, then I'm basically providing a force on it like this with, let's say, 10 newtons. You can measure it in some units like this. Now, it is quite rare. Sometimes you don't need to touch something and there will be a force. And one of those rare things, as you know, is gravity, right? Gravity is one of those rare scenarios where the Earth is not even touching the apple, and yet it's pulling this down. And you have actually the force of gravity, let's say G, or actually we have a better name for that, it's W, right? W for weight, acting on the apple, right? I sometimes will use G for gravity, W for weight. The textbooks will sometimes use FG or whatever. I don't want too many subscripts. Subscript is just a way of, I try to avoid it if possible. If not possible, I'll use it, but it's just a way to make something simple complicated, look complicated and confuse people. So that's that. All right, so this separates out the forces into contact forces and non-contact forces. So before we get dragged into this forest of technical details, remember what is our goal? Our goal is to find out how things move. And now we've convinced ourselves to find out how things move, we will need to find this thing called the net force on the object of interest, right? So this is our goal, to find the net force. So now, how do we do this? And the idea is you need to master free body diagrams. Okay. Right, so what is a free body diagram? Free body diagram is basically, let's say this is my object, and basically it's an object to write out all the forces acting on it, right? And in the past, so some students find this very easy, some students find it very difficult. If you are the latter, if you ever find it confusing to do free body diagrams, here's my tip. This is a way that makes it, if anyone actually had me as a TA for 3A before, I know there's a few of you, you'll hear me say this a lot of time already. There's a very simple way, a foolproof universal way to get this right, and it's very easy. You ask yourself two questions, okay? The two questions is, what is touching the object and what's not touching the object? Okay. The foolproof method. What's touching it and what's not touching it. And now when you ask yourself this, then you need to, you know that anything touching it will give rise to a contact force. So all you need is a arsenal of contact forces, sort of a checklist of contact forces. And fortunate for you is up until this point, there's only around a handful of them, around 4 or 5 that comes up over and over again. You just need to know these 4 or 5 and then apply them to the diagram. As long as you see that it's touching something, there's a contact force. And if it's not touching it, there will be a non-contact force. So a better way to say this is, ask yourself what's not touching it, yet still providing a force or a push or a pull. I'm just gonna keep it simple, right? So you ask yourself what's touching it and what's not touching it, yet still giving it a push or a pull, or i.e. a force, right? So, and this is even simpler. Non-contact force, actually, up until this point, you only learned one non-contact force, which is gravity. That's the only force that without contact can exert a push or a pull on something else. In fact, and after our halfway point in this class, actually after 2 weeks, beginning of week 3, you learn a new non-contact force, which is the electric force. Right? So if you have a positive charge and a positive charge, positive repels, and opposite charges attract. So that's again a non-contact force. By the way, if you know the answer on chat, do you know how many non-contact forces are there in total? Well done, Matthew. 4, exactly. So actually now that you learn gravity on Earth is basically mg, right? The force of gravity is. You've learned 1/4 of them. And then by the end of this course, you'll learn 2 of them, which is electromagnetic force. Actually, it might look like there's electric force and magnetic force. And then there was a big discovery in the 18th century that James Clerk Maxwell, with his famous Maxwell's equation, actually showed that the electric force and the magnetic force is the same thing. It's just different perspectives. This is, and actually give rise to the birth to allow Einstein to develop the theory of relativity. Einstein took that one step further and showed that if you have an electric force, and if you jump on a train and you look at the electric force from a moving vehicle, it will look like a magnetic force. That is one of the most beautiful discoveries of a very a great consequence in relativity. So electric force and magnetic force is literally a difference in perspective. If you're on a train, someone's magnetic force looks like electric force. We'll talk more about that to us. I don't know if we'll get a chance actually in this course, but maybe in 3C, you'll actually talk a little bit more about that. But towards the very end, we'll touch a little bit on this idea. What are the other two, by the way? They are basically the two forces that happens inside an atom, inside a nucleus. So they're the nuclear force. By the way, physicists are great at making up names. So we realize there's two types of force inside a nucleus. Turns out one is stronger than the other. And we call it the strong force and the weak force. Great job, right? All right, good. So let's give an example, right? So let's see. So if I have a box on a table, how do I analyze the situation? So first of all, you ask yourself, what is touching the box? This part, the table is touching the box. So first of all, identify your what you're interested in. Are you interested in the table? Or are you interested in the box? So the object of interest for us is the box in this case. So the table is touching it, then that means that it will have a force pushing it the other way. The table will be pushing it the other way. We call it the normal force. So normal force, because it's normal or perpendicular. Normal is the mathematical word for perpendicular, just to confuse people. Normal from the surface, and it will provide the force that way. Remember, forces are always on something, by something. On the object of interest, by the something is called the source. Right? So in this case, the normal, what is the normal force? Normal force is the force on the box by the table. Okay. The direction is perpendicular or normal. All right. Anything else touching the box? Technically the air around it, all right? But I'm going to use the famous statement in physics, which says, ignore air resistance. All right, so that's going to be very small effect. Technically, I should encounter that. In fact, actually, in the at the end of today, you'll see that we have to care about it a little bit. All right, right, so except air, nothing else is touching it, so you're done. The next thing is non-contact force. What's not touching it yet providing a force? Well, gravity, that's the only one you know at this point. Does it apply here? Yes, right? So you have gravity over here. So what's your conclusion? Well, if this stays the way it is, right? If it's not moving, so the acceleration is zero. Acceleration is zero is what we call equilibrium. So equilibrium means the forces must balance. So the magnitude, right? The value of n, whatever n is, if n is 5 newtons, g has to be 5 newtons. If g is 10 newtons, n has to be 10 newtons. So n equals to g, right? Notice this is a statement about the magnitude, not the direction. The direction is taken care of in the free body diagram. Couple of notes to draw a good free body diagram. Make sure all the force arrows must start from the center of mass of the object, your object of interest. Okay, do not draw things like this. Okay, this is what I call a physical diagram. So if someone is pushing the box here, someone is pushing the box here, good. There's nothing wrong with this, but it's not a free body diagram. In mathematics, you're only allowed to add arrows or add vectors when they originate from the same point. It's a small issue. Actually, one thing I actually don't like about this textbooks is they actually get this wrong. They draw free body diagrams like this. That is completely incorrect. Mathematically speaking, that's not right. Arrows should only be able to add here. And this will actually add to your confusion. Trust me, doing it this way, your problems will look very much simpler. Okay? So a common mistake on drawing free body diagrams is you forget to, either you forget to include a force that you're supposed to, or you include a force that is not there. So you made up an imaginary force that is not supposed to be there. All right, so why do I call this the foolproof method? Is because if you follow this rule, you will never invent a force that is not there, and you will always take into account of every single force. Let me give you an example. So imagine you're in space. So this is Earth. You're floating in space. Draw a free body diagram of this object of interest, right, of yourself. So you should ask yourself, what's touching yourself? That sounds wrong. Sorry, what's in contact with you? Nothing. So there's no contact force at all. So the only force is the non-contact force, which is gravity, right? There's not even air in outer space, right? So that is gravity, or let's call it weight. I'll sometimes use G, sometimes use W, so you get used to both, because one thing I want you to learn is do not get attached to whatever the symbol is. It's what it means that is more important. Now, this is one of the biggest misnomers when people talk about weightless. Because if you're in space, you're weightless, right? No, the weight is always there. The weight is mg, it's always there. What you're really feeling or actually this happens on Earth as well. Right? If you go on a roller coaster, or if you are free falling, let's say, so if you jump off a building, don't do that. But if you do, then you feel that weightlessness, but that's not true. If you follow what I just taught you, the weight is always there because the gravity is always acting on you. What you feel, what is a better word is actually normal forceless. All right, obviously this is not going to catch on, but this is what it is. You don't have a normal force. Why do we feel weightless? Is, let's say at the moment you are sitting on your chair like this, right? It's a terrible human being. You're sitting on your chair. What are the forces acting on you? So the forces is, well, you're in contact with a chair, so there's a normal force, and then there's gravity, right? So there's a weight over there. So now what you actually feel is normal force. You don't actually feel your weight. I don't know if you ever know this before. It's a subtle point. It's supposed to be taught in 3A, but a lot of time it's overlooked, right? So this is actually what you feel. The weight is always there. Hopefully that makes sense. All right, so this is one example of sometimes people start drawing extra forces on here. Another example is if I have a cannon and shoot a tennis ball out of it or whatever, right? If I ask you to draw all the forces on it, ignoring air resistance, ask yourself, what's touching it? Nothing. What's not touching it, giving a force? Gravity, right? Or weight, either way, right? So that's the only force that acts on it. It looks weird because it's actually, it's moving this way. The motion is going this way. But remember, the force relates to acceleration through net force equals to ma. In this case, the net force is just the weight. It's related to acceleration. So the motion, if it's moving this way, it's going to accelerate this way, which means the next moment it's going to tilt a little bit further down, and it's going to keep tilting down until it hits the ground. So that's the physics of this process. And it is a very common mistake that people will start drawing an extra force on here or here, right? They'll say this is the cannon pushing the force out. They are not wrong. Over here, when the ball is over here, yes, the cannon actually exerts a force that pushes it out of the cannon, as well as the gravity, right? It doesn't go away. But after it leaves in midair, the weight is the only thing acting on it. So this is a very common mistake of people inventing a force that is not supposed to be there. One last example is if something pushes on something, let's say, sorry, let me draw it the other way around. Let's say I have two boxes, one with 3 kilograms and one with 2 kilograms like this, right? And I try pushing on this with 10 newtons, right? So this is a physical diagram, not a free body diagram. So now let's draw a free body diagram. So I'll do this quickly. The free body diagram, now I have two objects of interest. I'm interested in the object with 3 kilograms and 2 kilograms. So this guy has a push. Let's give it a name. It's always good to give things a name. Called P, let's say push, right? So this guy experienced a push this way. So because the hand is in contact on this surface. What else is touching? Look at the physical diagram. What else is touching the 3 kilogram block? Well, the 2 kilogram block right over here. That's touching it, right? So this side will create a normal force pushing it this way. Okay. Anything else? Well, technically this should be a table, but for now, let's assume the gravity and the table's normal force cancel out. You guys are familiar with that concept, so it's not that important. I'm going to not draw that. Right? So assume things are moving one dimension. So that's all. Now, what about 2? What's in contact with it? So by now, I've repeated this enough times that you know that's the only part that's in contact with the 2 kilogram block. And the only force is the normal force. Let's clarify, since now I have 2 ends over here. This is normal force on from 3 on 2. Right? This is the normal force from 2 on 3. Okay. So let's say you push it and this guy is accelerating and the question asks you, what is the acceleration? I'm going to go through this very, very quickly since this is a recap. So now you ask yourself, well, what is the net force on 3? That should give me the MA for this block number 3, right? This block of 3 kilograms. I'm going to write this. I'm going to label the subscripts. I try to avoid subscripts if possible, but now I have to. It's not a choice. I cannot ignore it because as soon as I write the second equation over here, if I just write MA, now it's going to be confusing. Which M are you talking about? There's 2 different masses. If I write this, now I know I'm talking about mass of the block number 2 or block number 3 like that. So you need, if the mass is different, another common mistake is people forget to write down subscript, differentiating your variables, and then you substitute one into another when you're not supposed to. Okay? And the acceleration of 2. Now, of course, if you look at the situation, they should move together if I'm pushing it. So the acceleration of 2 is actually the same as the acceleration of the block number 3. So we can actually call it A, but I have a reason for dropping the label, right? The M, I cannot drop the label. What's the net force on 3? Let's call this direction positive. So it will be P minus N. N from 2 on 3. And this is the only force here is N from 3 on 2. Let me actually make this explicit. From 2 on 3, right? The M3 and 2 like this. Should I plug in the numbers? All right, I'll skip one step. I'll plug that in. It's always good to start with this step, by the way. Don't directly write this step. So start out writing down F equals MA, then you can plug things in. It will be clear to whoever's grading it what you're doing. All right, now, how do we solve this? Well, here is where we use Newton's third law. So hopefully you remember that. How does Newton's third law tells you, what does it say is if you switch the object and the subject, they will be the same. So these are called Newton's third law pairs, right? So object action equals reaction. So if the force on A from B is equal and opposite to the force on B from B on A. I don't know which way did I say it, but if you swap the subject and the object, that's a Newton third law pair. So now let's look at this. Is this a Newton third law pair? Yes, because one is N from 2 on 3 and the other is from 3 on 2. So if I'm switching this, so N2, 3, I'm going to be a little bit more lazy with the label now, is the same as N, I keep doing this, N3, 3, 2, all right? So let's just call it N. So P, the pushing force, what is it? Let's plug in the number, that's 10 newtons, right? So I can just use N. So the reason why the two N's are the same is because of third law. That's 3A, N equals to 2A, and now this is just shouting for me to plug this in over here. So so if I combine this, I have minus 2A equals 3A, right? So 10 equals to 5A, and A equals to 2. Right? So put in your units as well, right? Meters per second squared. That's how it's a quick example on how do you do this. Now, comment number 1, is you see how I do my problems is utilizing the power of SI base units. That's why I mentioned MKS in the beginning. If you use newtons and kilograms, notice when I substitute numbers in, I never substitute a unit. Because if I use SI units, my equations are so much cleaner. And at the end, all I have to do is just plug back in whatever the MKS appropriate unit is. It will always work. Right, this is a nice trick for you. Comment number 2 is the common mistake over here is people start drawing forces that does not exist. For example, if on block number 2, people will start drawing a pushing force over here. This is not right. The pushing force only acts on here. Okay, so some people think if I push this block, it will somehow translate over here. Yes, it does, but it translates through N. If you draw a P over here, you'll be double counting. So that's where the mistake is. So if you follow the 2 questions, you will never get it wrong. Okay. Okay. All right. So now that you are an expert in understanding how to deal with forces, let's address the final question. Why things float. Okay. All right. So let me actually call this chapter 1 of our course. We'll deal with the concept of buoyancy. Okay. The subtitle is Why Things Float. And if you do any reference reading, you want to refer to the textbook of chapter 13.1 to 2 and also 13.7. Just to save time, I'm going to go on a little bit further before justifying that. All right, so why do things float? So now, if I have something in water, let's say I have a piece of rock, let's start with a box. So if I have a box underwater like this, so what is touching this object? The water, all right? Let's say we don't know what the water does. What else is touching the object? Nothing else, all right? So so other than water, we have to keep that in mind. That will give a contact force. But other than water, the only other force is the non-contact force of gravity. So left alone, this object will sink. We all agree on that. The reason that this guy even have a chance of floating is because the contact force of the water is creating some upward force to balance out. Let's say this box has the right mass or whatever to float just in the middle, right? Let's assume that the water is creating an upward force, that upwards force that balance out the force of gravity or balance out its weight. And this is what we call buoyancy. Okay, so in fact, this is called the buoyant force in your textbook, just for your reference. So write FB, but if I start having FG, FB, F1, F2, things are going to be confusing. Let's just make things simple, right? Buoyancy, B for buoyancy. So buoyant force is the force. Buoyancy is the phenomena of having a buoyant force, of things floating. Okay. So this is the motivation of that. All right. So in fact, there's actually more than one ways to do. If I go back to answer why things float, there's actually two ways this can happen, and we'll address both ways. Today we'll address this first way, right? So the first way is buoyancy, and the second way is called dynamic lift. So airplanes fly because of the second way, which we'll talk about in 2 lectures from now. Okay, so buoyancy, it can happen in static or dynamic. Whether the thing is at rest or moving, it can happen. The dynamic lift, as the name suggests, is only when the object is in motion. Okay. So we're going to focus on buoyancy first. Okay. All right, so now that you know the basic, there's one question of, the next question, the natural question is how to calculate. So how strong is this buoyancy? Now, before jumping in that, let me address one quick way to actually answer this question of how things float is actually just look at the density of things. Okay? So let me introduce the concept of density. So let me introduce 2 quick concepts on density, on this before we show you the formula. So density is mass per unit volume. So this is the word definition for it. If any one of you are wondering, this symbol means definition. It means it's defined as. So if I just have the equal sign, it means the left-hand side is equal to the right-hand side. If I have the 2 dots, it means the left-hand side is defined as the right-hand side. Okay, so mathematicians have all these different symbols, which are actually, if you're lazy like me, it's very good in taking notes because you don't have to write the definition of density, or density is defined as the mass per unit volume, just write that. Right. So everything in physics, or most things in physics, has actually a word definition and an equation definition, or you can define things in word or define things in equation. Okay. So here's a quick study tip for you is, actually, let me write it out first. So density, we use the symbol rho, and it's defined as mass per unit volume. So that's very simple. Okay, and this, oops. So this is rho, pronounced rho is a Greek letter for R. Don't ask me why rho, that's a convention. Okay, let me give you a study tip in exams. In an exam, sometimes in the short answer question or in the test, I will ask you what's the definition of a density. So if you are asked, and anytime you're asked definition, you can either do the word definition, that's fine. You can define it by word, or you can define it by equation. Usually it's around 2 points. It's a 2-point problem like that, just to write that out. So if you write density equals to mass per unit length, you get 2 points. If you use the equation, you have to do one more thing, which is what I'm going to do right now. You need to define your variables. So this is density. So you should write where, let me write that a little bit properly. Actually, just to save time, I'll just do this. You can see my solutions uploaded. M is the mass of the object, and V is the volume of the object. So writing down this will give you 1 point. Writing down this will give you the other points. Because just writing out the symbols doesn't mean you know what it means. Writing down what the thing means, it means you know what the thing means. Okay, so this is how you will deal with definition questions. Okay, and as you remember, I just mentioned a little bit earlier, you shouldn't get too attached with what symbols you use, right? You see me swapping symbols all the time, and because there's a purpose of this, because if you use this textbook, you'll use one symbol. If you use a different textbook, you might use a different symbol. So partly I'm hoping to get you used to, train you to be able to be comfortable with that. And also I don't want people to get attached to memorizing formulas and putting too much emphasis on formula, but more emphasis on the concept. So for all these reasons, any formal exams you do, unless it's a multiple choice, which we are not going to do a multiple choice, that really tests your concept. Any definitions, if you write equation, you need to write out what the symbols mean. Because I could call density rho. Actually, some books actually do call density D. And that's completely fine. So if you decide to use D, just tell me what D is, and you'll get full credits as well. Okay, so right, so that's that. Now there's a nice concept called specific gravity, but a better word for it is relative density. So actually, in most scientific community, it's called relative density. In engineering, it's called specific gravity. All right, so what is this? So this is the ratio. This concept is the ratio of the density of the object. I know I should write out a full word, but now I'm just teaching and I'm just trying to write things a little bit faster. So hopefully after you understand the concept, you know why I'm doing this. So the ratio of the density of the object compared to the density of some reference material. And this reference material usually is water. Water when it's different temperature, it's a different density. Usually the reference is at 4 degrees, which is when water is the densest. Okay, so in equation form, so I just gave you the word definition. Specific gravity is the density of whatever object you're interested in over the density of some reference material. Usually this is, in most cases that we are going to be talking about in this course, it's going to be water at 4 degrees. Which is actually a good a very easy number to remember. In SI base unit, it's 1,000. Okay, the SI base unit is mass per unit volume, so kilograms per meter cube. Like that. Okay, so this is the definition of specific gravity. So as you see, specific gravity is really a very random word. Relative density makes more sense, but the textbooks use the word specific gravity. If you go to Wikipedia, you'll see that they'll tell you both are the same thing. Relative density, personally, I like better. So it's the density. So now it'll give you a very quick answer. You can easily answer, why do things float? So with these two concepts, you can easily answer, for example, if the object's density is larger than the water. So what does that mean? That means, i.e., the specific gravity is larger than 1, right? So look at the definition for specific gravity, right? If this is, so if I actually divide this over this side, you'll see that this ratio is larger than 1, like that, right? So specific gravity is larger than 1, then it will float. This little symbol here is the math symbol called implies. And so it will imply that it will float. On the other hand, if the object's density is less than the water, so the specific gravity is less than 1, then, so now you see the word where specific gravity come from, why engineers use this word is because the word gravity suggests if it's heavy or not, right? So if it's larger than 1, it's heavy. So that doesn't look right. No, I did say it right. I wrote it wrong. Sorry, it sinks. Right, sorry. Yeah, so the density is heavier, it sinks. It's very intuitive. Right, so the other way around, it floats. Okay. In principle, even if it's equal, it'll float. If it's equal 1, right, so it will float. Now, is this the end of it to the answer of why things float or how do things float? Not entirely, because it doesn't answer, this is not the end of the road, because it doesn't answer, for example, if I have a ship made of metal, right, made of iron or whatever, is that denser or is the water denser? Clearly the metal is denser, but this floats. So that is not the end of the story. So just because something is denser doesn't mean it has to float. So that's why I say this is a quick answer, but it's not a complete answer. Okay, all right. So also there's another scenario. If I start tying something that is less dense, right, with specific gravity less than 1, and I stick it together, tie it together with something with specific gravity larger than 1, and put it in water, which one wins? Does it sink or does it float? So these are the questions that the simple answer doesn't answer, and you need to analyze the buoyant force. Okay, so now let me give you the formula for buoyant force and show you how to use this. So the formula is this, rho VG. Okay, try to commit this to memory. And I'll put in 2 subscripts and I'll explain what that means. As you see, anytime I write out things in symbol, I need to define what each things mean. So this rho F is the density of the surrounding fluid. Remember the picture you should have, right? If you have something inside water, you want to draw if it floats, it will have gravity and it will have a buoyant force, right? So it is surrounded by water, right? So there's a contact force. I'm drawing the contact part of it, right? So the density of the surrounding fluid, the volume S means the volume that is submerged in the fluid, and G is the acceleration due to gravity, as usual, right? 9.81 meter per second squared. Okay. All right, so volume submerged is the most critical part, because if your object is like this, let's say it's only half submerged, right? So what should I use for volume submerged? Let's say I have a piece of wood, right? Sort of halfway floating like this. So the volume submerged is half of the total volume of that wood. Okay. If I have a let's say I have an iceberg. So if you sail out on Titanic or something, and you see an iceberg, that is, let's say, 20% floating outside and 80% on the bottom, like that, floating on water. What is the volume submerged? Well, in this case, this is the part you're interested in. So you need 0.8 of the ice, of the total ice. Okay, so that's how you get this value. Okay, so you should have two questions now. How do I use this? First question is, where does this formula come from? This magic formula, where does it come from? And how do I use it? Let me address the second one first. Let's say I have a piece of rock over here inside the water, and I put it on a scale. So we have a lot of experience that if you step inside water, you feel lighter, right? That's because there's a buoyancy force acting on you. So my question over here is, what does the scale read? So if the rock initially, let's say the rock is 10 kilograms, right? In water, how much does it weigh? This is a nice question, right? So what does the scale read? The scale will try to read the weight of this guy. So what we do is we do the free body diagram that we just talked about in the first 30 minutes of today, right? So you draw the free body diagram, everything should start on the center of mass of your object of interest. Ask yourself, what's touching it? First of all, the scale. The scale is touching on the bottom. So anything that is touching with the surface gives a normal force, right? What else is touching it? Water. That's the crucial bit that we're learning today. The new thing we learned today is the water provides a buoyant force, right? So so there's only two things touching it, the scale and the water. Water creates B, the scale creates N. Nothing else, right? Now you go to non-contact force. What's not touching it? Okay, gravity. So that's the only thing else we should put in. So that's my free body diagram. Now we can go out and write down a formula because this thing is in equilibrium. So if this thing is in equilibrium, that means that every force must balance, right? So let's say this is the positive direction, right? So N plus B has to equals to G for this to balance, to stay at rest, right? It's staying on the scale. It's not accelerating upwards or downwards. All right. Now we'll plug in all the numbers or plug in all the formulas that we know. Do we know a formula for G? Yes, right? Gravity is mg. Now what M of the rock? Okay, let me just label that clearly because we potentially have different variables over here. We have the water and we have the rock, right? And N, I don't know any formula for normal force. We'll just keep it N. So you just learned this formula for buoyancy. So it's rho VG, right? By tomorrow, you'll know this by heart, right? So rho F, I'll just recite everything over here first. So what is the fluid? The fluid is water, let's say, right? Water. So, so rho F is going to be water. Before I go that, let me try to establish what my aim is first. What is my aim? My aim is to find out what the scale reads. And remember, we talked about the guy in space, right? That's the reason why I talked about weightlessness and you sitting on a chair and you feel the weight. What you feel, your weight, like every time you stand on a scale, what it's actually reading is not your weight, as we just went through. What it's reading, the aim, what the scale is reading is really reading the normal force. But normally, just a quick detour, if you stand on a scale, right? You stand on a scale, let me draw a free body diagram and weight like this, right? What happens if you're in equilibrium, right? If you're not jumping up and down, N equals to W. Perfect. So the scale measures your weight nicely, but here it doesn't. There's an extra force. All right, so what does the scale read? The scale reads N. So what it reads is this. Let me actually write down now, it's row of water and volume of, actually the whole rock is submerged, right? So it's just the whole rock. Okay, it's just the whole rock. This is water, right? G. Okay. Okay, good. Now let's simplify things. Let's factorize out the G, right? So I have M, in fact, yeah, let's factor out the G. So I have this, sorry, minus rho water. All right, how about volume? There's actually a nice way to make the, so I have a lot of variables floating around over here. So it's good to eliminate some of the variables. So if you remember, we just mentioned that the definition is of density is mass per unit volume, right? So let me apply that to the rock. So if I put R over here, we see that this implies that the volume of the rock is the mass of the rock divided by the density of the rock. So I can put it over here like this. And the first time you see this, it looks a little bit magical, but the more you do it, this will become very, you'll see a pattern. Basically, every time the problems repeat this type of steps. So now you see another common factor, which is M. So you can pull that out, right? So let me actually pull out, right, mg in front. So I have this over here. All right, good. So let's look at this. So since the rock is clearly heavier, so you have actually both, you know, so the rock is heavier. Let's just make up a number. Let's say this is 5, this is 1, right? So this is a number that is less than 1. So 1 minus less than 1 is still a positive number. That's good. And this is something positive. That's the key thing. Okay, so 1 minus something positive, it has to be less than 1. So this whole thing is less than, right, less than mg, which is just the original weight of the rock. So my conclusion, you can see here, N is less than the weight. And that's why when you step inside water, you feel lighter. You don't feel your weight, you feel the normal force. Okay, that makes sense, because if you're sitting on your bottom right now, right? So what are you really feeling? You're feeling the chair pushing against you. You don't feel gravity pulling you down. You're feeling the chair pushing you up. You're feeling that normal force. If you're standing on your feet is, that's why when you walk a lot, you're tired, because your feet is feeling the force, all right? So let's give things a name. So N over here, right? So let me just conclude. If you've never seen this before, this is the symbol therefore in math. These symbols will help you take quicker notes as well, so that's why I'm introducing them. Let me just copy that out. All right, so usually if you have a homework problem or test problem, they'll actually give you numbers to plug in, right? So let's say the rock is 10 kilograms, and you can look up on your textbook, look at table 13.1. You might want to bookmark that, or get a screenshot of that to when you do your homework, because that has a table of all the density of stuff. It'll give you the density of rocks. I think it has a density of granite, a density of water. Density of water, I remember it. It's 1,000 with the standard SI units, right? So kilogram per meter cube. Density of granite, let me see, it's 2.7 times 10 to the power 3. Right. So now you can plug in all the numbers like this, all right? 10 gravity, 9.81, 1 minus, and you can actually calculate out. Right, so 1,000 over 2.7 times 10 to the power 3. That's actually 2,700, right? And plug that into a calculator. It will give you 61.7. Now you see my strategy is I don't plug in the units, because if I use SI units over here, everything that I plug in is SI units. This will automatically be newtons. Sorry for the confusion of a lot of n's floating around. And finally, let me introduce one more jargon, or 2 more jargons. This is called the apparent weight of the rock. Okay, so the apparent weight of the rock, it's basically it's basically the normal force you feel when submerged inside a fluid. And there's also a similar concept called apparent mass. Okay, so what is normal weight? So actual, as opposed to, you know, actual weight is mg, right? So what do you think apparent weight is? Well, so apparent weight must be, the apparent weight, let's call it W apparent, must be M apparent times G, right? So on the one hand, you have actual weight and actual mass. And on the other hand, you have apparent weight and apparent mass. That's the definition of apparent mass. So let me give the formula definition, the equation definition, right? So in principle, I can define it like this. But that's an ugly way to remember it. So let me not put a box around that. This is equivalent to a double arrow like this is the math symbol of equivalent to. A single arrow means this implies that. If a double arrow means this implies that and that implies this, which means both are equivalent. So it means equivalent to. These symbols are great when you take quick notes, by the way. Hopefully they're not too confusing. By the way, if I do this a lot, I use a lot of shorthands in my notes. If anything is confusing, take a screenshot of that, ask them on Piazza. I'm sure some great classmates will answer you for that. Or I'll also look at that, right? So a better way to remember it is the way I wrote down there. So hopefully it's pretty easy to understand what is these two concepts of apparent weight and apparent mass. And that is pretty much it. All I need to say. Okay. So this answers some of your questions, some of the questions already in the beginning that I posed on about why do things float, and now it also answered a question that you didn't ask is why do you feel lighter when you step inside water? Why do you? So the only thing I have yet to do, I'll fill in next lecture, is to explain this magic formula of rho Vg, why that comes about, and that. So before we dismiss today, let me ask you a question to think about. So with what I taught you today, there are a few things it'll be nice to think about is, if every time you step on a scale to now, what's happening? Even if you're in your room, if you take a scale, you step on it, and then the scale says, let's say it says 70 kilograms, a typical, roughly some average human mass, right? My question to you is this your actual mass or is this your apparent mass? Okay. Think about, are you submerged in anything, right? So, all right, so maybe I can give you half the answer already. Is the hint is you're submerged in air. Air is a fluid. Sorry if I didn't clarify. Fluid is just a collective term for both air, gas and liquid. Right? So collectively we call them fluids. So we're actually submerged inside, fully submerged inside air. You're in your room, right? So you're submerged inside air. So is it measuring your actual mass or apparent mass? Right? So that's half the answer already. So if it is the actual mass, here's your challenge. If it's the actual, calculate what your apparent mass is. If your answer to the first question is it is measuring the apparent mass, so if 70 kilogram, right, is it, if it's apparent, right, then draw a free body diagram, right? Here's the hint. Draw a free body diagram, write out the Newton laws like I showed you. By the way, it is always good to test your knowledge, because when you see me go through an example like that, everything looks very logical. When it's your turn to do it, you suddenly realize, oh, what do I do now? That's completely normal. Don't be afraid. That is the point of learning, right? So try this yourself, because if you don't learn. Of course, the homework will force you as well. This is not graded, but I think it's interesting. Yeah, calculate your actual mass if it is. Okay. You might need to know sort of the volume of your body. So if I had more time, I'll go through how can you estimate that. But just for now, I'll just give you if you ever heard of the joke that if you ask physicists to analyze anything about cows, the first thing they'll say is, let's assume the cow is a sphere. That's a very common joke, right? We're taking things and make it simple for us. And that's also related to what I said in my first day in lecture 1. We try to keep things very simple, so you shouldn't be afraid of physics, right? So let's assume a human body is a rectangle, cuboid. So that I can multiply all 3 sides, right? So roughly speaking, let's say a typical human is 1.8 meters tall times our width, let's say, is 0.5, half a meter from shoulder to shoulder, and our thickness is how much? If you take a ruler, measure yourself on the side, that's roughly 15 centimeters. Somewhere between 10 to 20 centimeters, let's say on 15 centimeters. Notice I immediately converted in my head everything to meters because I'm using MKS units, right? So this is the volume, right? So the volume, if you plug that in the calculator, it's 0.125. You can double check that, meters cube, right? So use this as your body, and you should be able to, because if you look over here, all you need is rho Vg, right? So if you know the density of air, I'll give you this as well. It's also in the table 13.1. The textbook. Density of air is 1.29 times 10 to the no, just 1.29. Yeah, with the standard SI units. So with this, you should be able to calculate either the actual mass or final mass. And final question is: assume if you move to a new planet, with that the density of air is larger. So if density of air is larger, does your and then you stand on the scale again. Does your either actual mass or apparent mass show, what will the scale read? So if you stand on this scale again with heavy air, right, denser air in this planet, what will it read? Will it read something that is larger than what it reads on Earth, or smaller than what it reads on Earth? All right, so here are the 3 questions that I will quickly test your understanding. And what I'm going to do is I'm going to actually write this out, these 3 questions out, and post it on Piazza as a post. I encourage you guys, just jump in and answer the questions. Whoever beats, whoever gives a good explanation of everything, explain why as well. Whoever provides good explanations, I'll endorse the answer. People can read from them. If someone answers, and you have a different take on it or a different way to prove things, you can also explain that on there. This is an exception. You can put full solutions there. Normally, I say for homeworks, you're not allowed to put a full solution, but this one is not a homework, so you can. And yeah, you can get extra credit for that. It's not graded, so feel free to ignore it if you want. But I think it's a good way to get some extra credit and also test your understanding at the same time. Have some good discussions. Yeah. All right, so that's it for today. Enjoy your discussion session later. All right, thank you very much, and see you guys tomorrow.